last time on we're all doing phase 1. Last time we started lecture 4, which was on fermentation. And we got all the way to example number 5. Now let's just recap the main thing that we did on Friday. Before we saw how we can count the number of arrangements of different objects, but if I had a collection of letters and some of them are identical, what do I do then? So the number of arrangements is equal to, what do I do if I have duplicate letters or identical letters?
6 divided by 3 factorial.
Sorry, say again?
6 divided by 3 factorial.
Sorry, I can't hear if you're talking, I can't hear. Say again, so I'm hearing you.
6 divided by 3 factorial.
6 divided by
3.
3 factorial?
2 factorials.
2 factorial. You sure about the 6?
1, 2. Yeah.
6 factorial.
Oh.
6 factorial.
Yeah.
The 3 factorial, so 6, I can count all the letters as if they're all different. 6 of them. Then I have to divide by the number of ways I can arrange the identical letters as if they're different. Just the p's among themselves, 3 factorial. Just the e's among themselves, 2 factorial. So this is my sort of more general way to count a collection of things, and maybe they have some letters that are identical. So that's where we ended last time. Let's move on to essentially just practicing this with number 6. Now I'll have the letters A, B, C, D, and 3 duplicate E's. And I have different restrictions. I want to arrange them. And the first restriction I have is no restriction. If I have no additional restriction, how many ways can I arrange them? Let's just say here number of ways to arrange them. Number of arrangements, number of ways I can arrange them, so the same. How many ways? Well, I have 1, 2, 3, 4, 5, 6, 7 letters. What do I divide by? 3 factorial. We're just doing the same thing over and over, just getting used to this slightly changed, slightly updated formula when I do have identical letters. And I don't care about what the calculator says. If you want to put this in, I leave it like this to show that I know how to get to the answer. What is the restriction they give me in the second part, B? Now I want A and B to appear next to each other. So now we're combining this idea with identical letters with the previous type of question we saw where I want some letters next to each other. So now I want the A and the B next to each other. So let's do this one in steps as well, emphasizing the steps. What could step 1 be? Following what we did way back in example number 2.
Blue letters. Blue letters. Super letter.
I make a super letter. Let's say here blue, A and B together. And I also have the C, the D, and the 3 E's. And the range. So how many ways can I do that? Well, now I have 1, 2, 3, 4, 5, 6 letters. So 6 factorial. And 3 of them are still identical.
What about the A and B? Do you arrange those two?
Well, that's just step one. Just doing one step. I need to follow that by another step because you say correctly, well, what about the A and B? I just glued them together, but they don't have to be in that order. I glued them as A, then B, but that doesn't cover all the arrangements that I can get. So I need to follow that by step two, essentially arranging, let's say here, inside the super letter AB. Number of ways to do that. Well, there are two of them. How many ways can I arrange two distinct letters? 2 factorial. So the total number of ways to complete this experiment, which is arrange these letters under the restriction that I have the A and the B together, I broke that up into 2 steps. Step 1, where I move them as one, A and B together, followed by step 2, where I arrange everything inside this glued letter, and that completes my experiment. So the basic principle of counting says number of ways for the first step times number of ways for the second step. And again, if for some reason you have different steps or do them in a different order, as long as one is one followed by the next, followed by the next, completing my own experiment, I just multiply them at the end, however you broke it up. Yes?
For the same letter, if it was BB, can you still arrange in 2 ways? Or is it since it's the same letter, it doesn't get arranged?
Does that come up maybe? That's coming up in C.
Okay.
So let's do C. So the question is, what if these guys aren't different? Well, if we look at number C, 6C, there I want all the E's next to each other. So that would be exactly that kind of question. So let's just check if there are any questions on A before I erase it. Are there any questions on the steps for number B when I glue the A and the B together? So it's a combination of the ideas that we've seen before. Let's look at the restriction in C, where they want the 3 E's next to each other. Now these are steps again, and our next examples will shorten it a little bit. So again, step 1, I'm essentially going to arrange my glued letter, which is now this. I have an A, I have a B, a C, and a D. When I glue them together to make sure that they are always next to each other, those are my new set of letters. How many ways can I arrange them? 1, 2, 3, 4, 5 letters. And they're all different. They're all different. So just 5 factorial. Technically, there is a step 2. If I follow what I did in part B, same way of thinking, same steps. What is my next step? I have to arrange inside the 3 E's, the super letter. I have to arrange inside that super letter. Just as I did for the A and the B. How many ways can I arrange those 3 letters? Well, there are 3 of them. So my formula says 3 factorial, and then check for duplicate letters or identical letters. There are 3 of them that are identical. So the formula still works. I don't have to see this as anything else. But if you want to write 1, because 3 factorial is 6, 6 divided by 6 is 1, you're perfectly correct. I'm just sort of emphasizing that this isn't anything different. And it's also covered by my formula when I have identical letters. I have 3 letters, and 3 of them happen to be identical. Any questions on step 2? So I can then say, well, I needed these 2 simpler steps on the way to completing my experiment. So the total number of ways to arrange these letters is 5 factorial times 3 factorial over 3 factorial. Let's put a little box around them. And again, you can write that in a different way. Depending on how you see step 2, you could write 5 factorial times 1. You really don't have to write the 1 if it's really obvious to you, but I'm emphasizing the step, that there is a step 2. I don't want to just omit this, because in this case, there isn't really anything to do. Shuffling the 3 E's doesn't give me anything new. But in general, there would be this second step. So even if you include it for the sake of being complete and detailed, your answer might look different, but it's the same. Any questions on part C? Does this answer your question?
Yeah.
So it doesn't, the steps aren't affected by what's inside the superlayer. It's the number of ways for the step 2 that depends on that. Yes.
So if that, like EEE was say like EFE, the answer, the number of
Well, this
places
would change your
factorial to 2 factorial?
Because I then only have, if that guy happens to be an F, doesn't matter how I glue them. When I shuffle these guys inside, then I only have 2 identical letters. So that will change to a 2. So it does depend on the composition of my superlayer. But the idea of keeping things together, that's still the same. Okay. Let's see the sort of the reverse of this gluing idea, and that's when I'm trying to keep letters away from each other. In D, the B and the D do not appear next to each other. So I'm following very similar restrictions as we did in example 2, except I now have this duplicate letter thing included. The B and the D do not appear next to each other. What is my strategy here? Well, for the sake of being complete, let me define a set. Let's call it capital A. Let that represent the set of arrangements. After a while, we won't be this detailed, but for now, it's worth emphasizing what we're doing. And once we get used to it, we can relax the detail a little bit. Let A be the set of arrangements that they're looking for, essentially. Let's say that have the B not next to the D. There's only one of each. So the B has to not be next to the D. If I visualize it with a Venn diagram, just for my own sake, to be as clear as possible on what strategy I'm going to use here. Let's say the circle represents the set A, all the arrangements that I'm looking for. Now, it's a good rule. It's not, no rule is going to work for every single case, but it's a good rule when I have something that I want to separate from something else. To just ask myself, is it easier to try to count this directly, or maybe count the complement, everything else? So, if I want the number of arrangements that have what I'm looking for, the B and the D separated, I can do that indirectly by counting everything without any restriction and take away the complement. So let's say here, this is no restriction. And this is what? Where's the complement? I have to say it in words first, so that I have a clear idea of what I'm trying to count there.
B and D next to each other.
What is the opposite of B not next to D? Well, B next to D. B and D next to each other. So let's do that here. Well, we did this one already. That was part A, where I have no additional restriction. I had A, B, C, D, E, E. That was 7 letters. And I had 3 identical letters. So that's the first part of this. I have 2 parts in the indirect approach. But it's not really more work because this no restriction one is always going to be straightforward. It's really only this guy. So I choose whichever one's simpler. This guy, the complement is simpler because now I want things next to each other and just did 2 examples like that. And those are reasonably straightforward. Now I want the B and the D next to each other. Well, we did this 2-step process twice now, so I'll just do it in one go here. What is my first step when I want to count this now? Glue them together. So let me write it on the side here. If I glue them together, I have a B and a D. I have the A, B, C, and 3 E's. Good to just write down. Okay, these are my new letters. I have 1, 2, 3, 4, 5, 6 of them. Are there any identical ones? Yes, the 3 E's. But I'm not done. That was just my first step. I have to follow that by the second step, which is arranging inside the super letter 2 factorial. So even though I'm combining these steps, I'm not writing step 1 and step 2. There's nothing wrong with it. But I think we'll naturally move away from that and doing it in one line as we get more comfortable. But I'm still motivating where this comes from. I'm still defining my step. I'm visualizing what's happening. I'm saying this is my approach, the indirect approach. I just tell myself here this is what each one represents, and then I can go and count. So I'm still motivating clearly what I'm doing. It's not as if I'm just writing these numbers down. So depending on your comfort level, you can do them in steps more clearly, saying to yourself what you're doing. And as that starts to feel more natural, you can do it in one line, in 2 pieces. Because here I require that I need to be able to tell myself and see clearly what are the steps, because I'm not writing it out in that much detail. So be careful to jump to this before you're perfectly clear on what the steps are. We have more than enough time in any test or anything that there's always time to write everything out clearly so that you're always aware of what you're doing. Any questions on number B? So here there's no real math involved here in the sense of symbols and equations and stuff. Sure, that's an equation if you really want. But it doesn't ever really get messy or intimidating. It's more the structured way of thinking that we're emphasizing and practicing here. So number 7 and 8 really, they're only there to lead me to what we're going to talk about on Wednesday. So let me get that out of the way. And then, depending on how much time we have, we can look at some of the homework questions and just practice a little bit to get more comfortable. And because we did so much on Friday, that we can relax a little bit today, which is always good. Relaxing on Monday, it's a good tone for the week. So at this point, we can do absolutely everything on the homework, including number 9 and 10 that I said maybe best to wait for today, where I'm still arranging, but I have duplicate letters. So let me just talk about number 7 and 8. Number 7 asks, something simple. In how many ways can 5 people be selected from a group and seated in a row? So we're sort of, this is the introduction to the next lecture really, but in the interest of saving time, I do it here, and then you can think about it a little bit, and let it be processed before Wednesday comes. I want to select 5 people and then arrange them in a row, and I have a group of 8 people. So, what's my experiment? My experiment is putting 5 people in a row, and then I'm done. So there's a part selection and a part arrangement. So I'm ending up with a row, an arrangement of 5 people. How many choices do I have for the first seat, or the first position? I have 8 choices. Because there are 8 people to choose from. So I sit down, see the person here in the first chair. How many choices do I have for the next position? 7? It's not overly challenging. And then I have 6, and then I have 5, and then I have 4 people. So not everyone's going to sit. I only have 5 chairs, and I have 8 people. So the other 3 people are going to go and find their own seat, or stand, or something else. I'm not interested. I only have seats for 5 people. So the number of ways to do this is 8 times 7 times 6 times 5 times 4. I'm sort of taking a step way back to just the basic principal accounting examples. Everyone happy with it? Pretty straightforward by now. No duplicate letters, no nothing like that. So let me just emphasize here, we are selecting and arranging all in one. All in one. By having a limited number of seats, I'm selecting some and I'm arranging them in a row. So the only point of this example is that we can write this in a more convenient way. So, do you agree that I can write this as 8 times 7 times 6 times 5 times 4, 3, 2, 1, divided by 3 times 2 times 1? 8 factorial divided by 3 factorial. This isn't 8 factorial. I need to go down all the way to 1. And because I'm attaching numbers here, I need to cancel them as well. So my original numbers were 8 people and 5 chairs. And there's a 3 here, so let me just get rid of the 3 by writing 8 factorial. That 3 is there because it's 8 minus 5 factorial. Just relating everything to the 8 to the 5. Now, it's not crucial if I'm perfectly happy with this. It's really just an observation that helps me on Wednesday. Any question on where this comes from? There's nothing wrong with writing this. I'm just sort of observing that I can write this in a more concise way. What if I had 100 people and 50 chairs? Then this is going to become really lengthy. But I can write it in a short, concise form. So if you remember what you may have done in high school, this is that P thing that you might write 8P5 and put the 8 to the 5 in different positions depending on the school and what your teacher liked. I think maybe they call that a representation. There it is, it's an arrangement. But you don't have to ever remember this. It's best to forget it actually. Just say, is familiar when you think about it, yes.
Do we have to take into account that there's also 5 seats?
Yes, I did, fine.
So if you're choosing 8 or 5 people out of the 8,
Yeah.
then there's also 5 chairs, and they can be seated different ways in the chairs.
Yes, but by doing this, I am arranging them.
Okay, so you don't have to worry about them multiplying it by like 5 factorial.
No, it's already arranged. I've already arranged everything. This is my first basic counting principle example, where I'm arranging. And because I have fewer chairs than people, I am essentially selecting 5 people. Okay, so if I generalize this to a formula that you don't need to remember, I just want to write it on the board at some point. I'm never going to ask you to reproduce this. If I sort of generalize this to not necessarily 8 people and 5 chairs, but I'm selecting R people from a group of N, a larger group N. So let's say here I have N people and R chairs. Could be 85, might not be. What happens then? Well, 1, 2, 3, all the way to R. So how many choices do I have for the first position? I have N people to choose from. How many choices do I have for the next position? I have 1 less, and I represent that by N minus 1. And then N minus 2, and so on. Just out of curiosity, what is that number there? Is it N minus R? Careful, it's not crucial. Sort of out of curiosity.
So why is it N minus R?
No, I'm asking, is it?
The N minus R plus 1.
Does it work for this? If N is 8 and R is 5, is this N minus R? No, it's 1 off. It's 1 more than that.
The power work?
So I have to have a plus 1 here to make it fit with actual number example. And you can try different numbers. It's only going to be 1 more than N minus R. Again, don't freak out. I'm never going to ask you to reproduce this. I'm just, I do want to write it at some point on the board. So, the total number of ways to do this, to select and arrange, is then N times N minus 1 times N minus 2, all the way down N minus R plus 1. Now, because I don't have specific numbers, this is of course going to look a little bit worse than this one. As soon as I have specific numbers, that always looks nicer. And I can write this as N factorial. Oh, let me not skip this. Let's not skip this. I can write that as N times N minus 1 times N minus 2 all the way down to 1. What do I have to divide by then? So that when I cancel this tail that I'm attaching, I do have that. I have to divide by N minus R, N minus R minus 1 all the way down to 1. So if I bring this all together, I get N factorial over N minus R factorial. And this is the formula from high school, NER, depending on where you put the N and the R. The permutation formula you did in high school. But again, I'm just sort of linking it to show that this is familiar when you remember what happened years ago, but I don't need to remember this. If you ask me why, then I'm going to go off on a rant about how the high school is teaching you the wrong way and all those things. So I think it's good news. No need to remember. I'm never going to write this P, but I need this to help us on Wednesday. So at least if you have an idea of where this comes from, I'll refer to it on Wednesday and then we'll move past it. Any questions on this? Yeah.
I don't understand how you have the n minus r plus 1. What do you want?
Because of this, guys. If I have R position, chair number 1, chair number 2, chair number 3, chair number R. And I have n choices and it goes down by 1 every time. How many choices do I have here? How many people do I have left to choose from as last position? When I think of my example where n was 8 and R was 5, it was 8, 7, 6, 5, 4. This was 4. So it's not 8 minus 5, it's 1 more. Don't worry too much about this. I know it's not obvious to everyone.